Today's system-on-chip designs interact more and more with the real world around us, and they need more analog mixed signal circuits on board to do that job. These AMS circuits tend to have multiple modes and states, all programmed through digital control logic. And as an early research paper from Semiconductor Research Corporation showed, it's bugs in these AMS blocks themselves or the surrounding interface logic that accounted for up to 50% of chip redesigns. But AMS blocks are not easily integrated into a traditional SystemVerilog testbench. For one thing, they operate in the continuous time domain. For another, issues revolve around things like voltage levels or signal noise or current leakage. In this webinar, we'd like to show how to seamlessly integrate a digitally programmable analog bandpass filter into a traditional SystemVerilog OOP testbench. And we'll be using Scientific Analog's X-Model software, a Linux-based plugin extension to popular commercial logic simulators like Excellium and VCS. We've got almost 80 slides to cover, so let's divide things up into 10 sections. We'll start by looking at the test bench organization and the DUT itself. We'll drill down into key components like the scoreboard. We'll even look at writing analog assertions using SystemVerilog syntax. And we'll wrap up with a dozen handy guidelines. Section 1, let's look at the test bench and the DUT itself. The purpose of any test bench, of course, is to apply input stimuli to the DUT and check the output response. We'll use the term transaction to indicate a given set of input stimulus and output response. And we'll encapsulate that transaction inside a suitable data packet. At the highest levels of this OOP test bench, the sequence object generates an untimed series of transactions and sends the corresponding data packets down this first in, first out mailbox into the driver. The driver is a lower level object which is aware of DUT pinout and timing, and it breaks up the packets into fields, sends those fields over the wires of this interface bus labeled diff to where they can reach the DUT inputs. On the other side, the monitor object does the reverse. It collects the data coming out of the DUT over this interface bus MIF, reassembles that data into packets, and sends them on up into the scoreboard. It's the scoreboard that makes the test bench entirely self-checking. For each transaction, it compares the actual filter gain against the expected filter gain derived from SPICE simulation data. At the lowest levels of the test bench, we found it convenient to encapsulate all the analog behavior inside a fixture submodule. That includes the DUT itself, a few X-model primitives used to generate the input sinusoid to the DUT, and a few other primitives that measure the peak-to-peak amplitude coming out of the DUT. In this fixture, we also encapsulate signals of X-bit type or X-real type. These are X-Model's custom SystemVerilog data types that enable it to do fast and accurate simulation of analog quantities in a conventional event-driven simulator. We designed the DUT using a tool familiar to any analog designer, Virtuoso. Here you see the DUT consisting of about 24 transistors, and it's centered around a 9-transistor op-amp. It's surrounded by an RC feedback network, and transmission gates within the feedback network enable us to switch in resistors and capacitors into series or shunt combinations, and that enables multiple passband and gain modes for the filter. The transmission gates are all controlled by this digital logic shown here. By the way, Once you've installed Xmodel, you'll see this Glister toolbar and the corresponding Glister menu, enabling you to do routine tasks like view analog waveforms over time. Everything is designed in this example in a 45 nanometer process design kit. This slide is a more intuitive view of the programmable bandpass filter. We can see the 4 control bits coming in from the left. The most significant bit controls the bypass state. If it's deasserted, then the filter is in normal operation, and the 3 lower order bits are used to switch resistors and capacitors into and out of shunt combinations, giving us the 8 different passband and gain modes. However, when this most significant bit is asserted, it puts the entire filter into bypass power down mode. The op-amp is tri-stated. It's cut off from the supply voltage and from the bias voltage. And via this transmission gate, there's a bypass path directly from input to output. Here's our simple verification plan to verify the programmable bandpass filter. The white rows correspond to normal filtering operation, and the blue shaded rows correspond to bypass power down mode. We'll use constrained random verification techniques to apply random frequencies in this design range to the DUT. They'll be uniformly distributed. And we'll also apply randomized modes, any of the 8 modes. And we'll show later how to make these cyclic to minimize repetition of the modes. The scoreboard will compare the actual gain versus the expected gain. One of the compelling reasons for using a SystemVerilog Testbench in the first place is to generate coverage metrics to indicate how thorough our Testbench code is. And we'll see in section 8 how to achieve 100% coverage of not only the individual frequencies and modes, that's pretty straightforward, but also the cross product. And we'll eventually reach 100%. In bypass power down mode, we can still get some checking done using analog assertions. We'll see 2 assertions. One asserts that the current during power down drops into the nanoampere range, the leakage range. Another assertion asserts that the bias voltage should recover and reach its nominal value of 700 millivolts plus or minus 50. We'll cover that in section 7. Here's our first look at SystemVerilog code. We want to convert this table of 8 different modes and their binary encodings into a SystemVerilog data type, a custom type definition. So we enumerate the modes by specifying their symbolic names and their binary encodings. And just to demonstrate how seamlessly Xmodel integrates with all SystemVerilog syntax, we've used escape names. The leading backslash and trailing space make illegal characters like this hyphen okay. And so mode 7 corresponds to a bandpass of 20 to 80 kilohertz with a nominal filter gain of 1, and its encoding is 111. Once we've packaged this type def and imported it, higher level object code can refer to the modes by their symbolic names. When the most significant bit is high, on the other hand, the filter enters bypass power down. Let's look in more detail at the data packets. Each packet corresponds to a given transaction. So it includes both information on the applied frequency and mode and the outputted peak-to-peak sinusoidal amplitude. We found it useful to include a tag as the first field in the packet. Every new transaction, we increment the tag number, and that helps us ensure that we're comparing the same packet going into the DUT with the corresponding packet coming out of the DUT. Here's our packet class code. We've spread it over 2 slides. On the first slide, we'll focus on the input variables. The second slide, we'll look at the output variables. And this is combining all the information into one packet is in sync with one of Cliff Cummings' guidelines published in his paper, UVM Transactions. So we've talked about the tag. Let's look at the mode. The SystemVerilog qualifier rand declares this as a random variable, and the simulator can then randomize it every time we call the .randomize method, and we'll get one of the 8 possible mode values. Here's the integer frequency. SystemVerilog can only randomize integer valued quantities, so we'll start out with an integer frequency from 10 to 120 kilohertz, and we declare that as a rand. We'll see in a moment how to convert that into a real. Meanwhile, though, we've added a named constraint, frangecon, to ensure that the solver inside the simulator only chooses random values of frequency within this specified range. Here are the output variables. They're ordinary real SystemVerilog variables, PPA in and out, measured in volts. And so those are the fields within our data packet. The packet has one method. SystemVerilog includes a built-in post-randomize function, which you can customize. It's automatically called after every invocation of .randomize. So we've customized it to take the integer frequency, let's say 27 kilohertz, we multiply by 1,000 and cast it into a real type. So freal is now 27,000.0 hertz. And we'll see in the next section how to convert this randomized real frequency value into an actual sinusoid that we can apply to the DUT. This slide shows in more detail how the DUT interfaces with the packets coming from the driver or reconstructed by the monitor. The fields from the packet are sent over the signals making up this interface bus. They enter this interface port, and inside the fixture, they're applied to the DUT inputs. Similarly, on the monitor side, the signals coming out of the DUT, such as PPA out, enter this interface port and travel over the interface bus MIF to the monitor, which reconstructs them into data packets. One frequently asked question, how does a hardware bus hook up with an abstract object like a packet class? Well, classes have no ports, and so we use a SystemVerilog virtual interface, a class variable, which, as we'll see, gets bound to the interface bus diff to make that connection. Here's the interface bus code. It's basically a bundle of signal declarations, starting with the integer tag, including the mode of enumerated type, the integer and real versions of the frequency, and the peak-to-peak amplitudes in and out of the filter. We can instantiate this interface bus by name as diff on the driver side. And we can also bring in a clock signal and a reset, which are defined at the very top level of our test bench and are spliced in as ports. Once this interface bus reaches the interface port on the fixture, we can reference any of the available signals using dot notation. So it's this interface bus diff that carries the packet information into the fixture and from there to the DUT. Let's mention a few more frequently asked questions that we'll answer in the sections ahead. How do we actually convert that randomized real frequency variable, f real, into an analog sine wave? We'll see that in the next section. Question B, how can we measure the peak-to-peak amplitude of the sinusoid that leaves the DUT, especially measuring it over time after we're sure all the transients have died away? We'll answer that in the next section. And finally, what enables a logic simulator like VCS or Questa or Excellium to quickly and accurately simulate analog behavior? Well, we've already mentioned the data types XReal and XBit, and we'll see those in more detail in the sections ahead.